In the last video, we looked at the basic operations of arithmetic, algebraic operations, addition, subtraction, multiplication, and division. And we looked at the most foundational properties they have. So the simplest possible properties of especially addition and multiplication. Things like the associative property, the commutative property, and the distributive property. So now what I want to do is to look at the consequences of those fundamental operations. And really the consequences will be all the pieces of algebra, the manipulations that you've seen many times before. And what I really want to do here is go through really a list of something like 10 to 11, maybe more, maybe 12 different pieces of algebra that you will have seen many times before. And really I want to do this because no matter what you're dealing with, no matter what complicated expression you're trying to manipulate, I think every single situation should always involve just doing the ones I'm about to describe to you slowly and methodically, one at a time. That's how I do algebra. That's how, well, all university professors do algebra. It's slowly, methodically, one step at a time without jumping 15 steps. Over time, when you get really good at these things, you can maybe loosen up a bit, but it's still really good practice to carefully write every step and think, what is the specific piece of algebra I'm using at every moment? So let's start off with the following. Let's start off with a really common piece of algebra that causes a lot of problems. It's one of the first interesting pieces that you learn. So if I take the sum of two things and I multiply them together with another sum. Okay. So what I'm going to try to do is to come up with a different way of writing this down if you want, right? This is an expression. It's the product of two things. The two things happen to be a sum. What I want to do is to try to expand this out. And the reason I want to expand it out is because, well, the A, B, C, and D may not be as simple as just easy numbers. They could be quite complicated expressions. I may need to expand this out to make things a bit more obvious. Now, it looks very much like what went into the distributive property, right? The distributive property was something multiplied by a sum can be expanded. So let's basically apply the distributive property here. So let's apply the distributive property where I break this into two pieces and imagine this is a single thing on its own. So that would be A multiplied by C plus D plus B multiplied by C plus D. So that's the distributive property applied once. But you see now I can do the distributive property again. So doing it again would give me A multiplied by C plus A multiplied by D plus then what would be B multiplied by C plus B multiplied by D. So actually quite a complicated looking expression. So let's take a moment to go through each of these pieces quite carefully and think if there's an easy way to remember what happens. So first of all, this here. So what do those correspond to? They correspond to these two here. Okay, so these are the first from each. So let's write first here. Let's do the next one. Let's do orange. So A times D, what does that correspond to? Well, that corresponds to the two outer ones here. So let's write outer. Then what do we have? Well, B times C, that would be this. So this is these two guys. So these are the two inner ones. Okay. And then finally, let's go crazy, let's do magenta. A times D. So that corresponds to, what am I saying? Wrong. It corresponds to B times D. And that's the two last. So this is often shortened to an acronym, namely FOIL, F-O-I-L. So this is something that you may well have seen, but it's worth going through it carefully now. But what I would really say is rather than just memorizing this FOIL business, I don't think it's a good idea in general just to memorize acronyms or silly little methods to do something. It's better to understand why things are truly true. That will certainly mean it will be retained in your mind for much, much longer. And the reason it's true is the distributive law, right? When I think about multiplying this, I don't think FOIL. I think it's the distributive property done, well, 3 times. The distributive property. Times 3 if you want, right? So it happens 3 times. Once in the first equality and then twice in the next. Okay, so let's do a very specific example. So let's do a very specific example. Let's go for a numerical example, nothing crazy. So all the way along, I'm going to do on the left kind of a general principle, and on the right, kind of a specific example of it happening. Sometimes it'll be very simple. Sometimes they'll be more like the types of algebra you'll see in the courses you do. 3 times 5. Okay, so before we do anything, let's work out what this actually is. So the 2 brackets, or the 2 parentheses, this is 5 times 8, that's 40. Okay, that should be the answer. But then let's do the first, the outer, the inner, and the last. So the first, 2 times 3, plus the outer, that's 2 times 5, plus the inner, 3 times 3, plus the last, 3 times 5. What does that come out to be? That comes out to be 6, plus 10, plus 9, plus 15. And adding all this together gives you what? It gives you 40. Fantastic. That's exactly what we hoped. We know the answer is 40. It's 40. As you'd expect, this is a specific example of a general phenomenon described by the right-hand side. A really important example that comes out of this is also the following. If I take a plus b times a minus b, and I take the time to do this, well, I'll get an a squared, then I would get a minus ab, then a plus ab, then a minus b squared. And the 2 central terms would cancel out. I would just be left with the f and the l if you want. So in that case, this turns out to be equal to a squared minus b squared. This is a really important algebraic equality. It turns up all the time, and it's something you need to be pretty familiar with. And it's called something, it's called the difference of 2 squares, unsurprisingly. So the difference of 2 squares. So a very important piece of algebra. Something to say as well is a warning. I'm going to try to, as I go through this, come up with or show you very common mistakes that I see students making. The most obvious mistake here is the following. So warning here. If you do a plus b times c plus d, then in general it is not, absolutely not equal to ac plus bd. This is a very common error, right? This can't possibly be true because it would break the distributive law. So this is not correct. And let's just do an example. If I was to do this with the above example, it would be a 2 times 3 plus a 3 times 5, which is 6 plus 15, which is 21. And that, of course, is not equal to 40. It's not right. Now, here's a general rule for you. If you're doing a piece of algebra, some simplification, and you feel a bit shaky about it, always just substitute in some simple numbers to see if it works. With overwhelming likelihood, if it's not correct, you'll get something going wrong. You'll get a non-equality turning up. Okay, so this is exactly this, right? If I write down a plus b times c plus d, say, well, let's check it with 2, 3, and 3 and 5, doesn't work. So it cannot be a correct piece of algebra because algebra is about general properties that are always true for numbers. Okay, so that's a very important piece of algebra. Next, a hugely important skill you need is the ability to manipulate equations. So an equation is an equality between 2 things, understandably from the terminology. Something equals something else. And a foundational principle in mathematics is if 2 things are equal and you do the same thing to both of them, it should remain equal. It's not true of everything, but it's true of equalities. So that means we're able to manipulate equalities using algebra, as long as we do the same thing to both sides. So let's do kind of a really simple example. Let's do A divided by B is equal to C. Imagine I've got a situation like this. Well, if I was to take this equality and multiply both sides by B, what would happen? Well, on the right-hand side, I would just get B times C, and on the left-hand side, I would get A over B times B. And by rearranging things and manipulating them, that would have to be equal to A itself. The B would cancel if you want. So this is exactly the same statement as this. So this if and only if symbol, is this what this is? That's what this is. If and only if. So this symbol is used when two statements are completely identical. So this statement guarantees this statement, and this statement guarantees this statement. And I do need to be a little bit careful. It's not quite correct as it stands. There is a bit of a problem. I can't have B is equal to 0. B equals 0 would make sense on this side, but it doesn't make sense on this side. So I need to be a little bit careful. In this, I'm making the assumption that B does not equal 0. Okay. So these two statements are completely equivalent to each other. So let's do a quick example. Let's do, imagine I have x over 2 is equal to 3. And I want to know what x is. So x represents some number. So I ask myself, what number would make this true, this equality? So I can see the following. Well, 2 is non-zero, that's good, so I can apply this simple business. So this is if and only if. So multiply both sides by 2, cancel out if you want, however you want to understand this. This is 2 times 3, sorry, that's equal to 6. Fantastic. So I always think about this as essentially moving a division to a multiplication, right? You're moving it back and forth. But the actual formal way of showing it's multiplying both sides by B if you want. Okay, so we've got something very, very similar for addition. If this is true, this is if and only if, with no restrictions on B at all now, A is equal to C minus B. So why is this true? Well, it's true because you take both sides and add minus B to it, and then B plus minus B is 0, 0 plus anything is 0. So we're just using our fundamental properties to simplify things, and this is what we get. Okay, so let's do a quick example. X plus 4 is equal to 9. This is if and only if x is equal to 9 minus 4, that's equal to 5. Nice example. When I was learning this one especially, I don't know if I fully condone this, but when I learn this, I always think change side, change sign. Because if you're positive on one side, you become negative on the other, and vice versa. That only works with addition, right? So don't get confused about multiplication, but that's how I remember this. Okay, so these are ridiculously important. They are the bedrock of how we manipulate equations, right? Doing these over and over again. You may have complicated expressions where you need to do this multiple times, but this is an incredibly important single step. Okay, next. One that's incredibly simple, but it's worth pointing out. If I multiply A by 0, it's always equal to 0. It kind of feels obvious. It follows from your fundamental facts. There's no point in going through a detailed argument why. It's true. There's not really any point in giving an example. It's so simple. Something to be aware of more than anything else. So if we take minus 1 and multiply it by any number, it does what you're very familiar with. It gives you just the negative, minus A. Very nice. In particular, minus of a fraction is minus A divided by B, or it's equal to A divided by minus B. They're all the same. Okay, so useful things to know. So as a quick example of this, let's do a bit more complicated, let's deal with an expression like this. So here x is representing a number, can't be equal to 1, otherwise I'd be dividing through by 0. So let's just think about what this would give me. Let me write it from two different perspectives. This is minus 1 times x minus 2 if you want. It's the negative up there. Then you can distribute that, rearrange a little bit. Minus 1 times minus 2 is 2. This gives you 2 minus x divided by 1 minus x. But we could also do the following. We could also put it on the bottom, right? So we could also do this is equal to x minus 2 divided by, well, minus 1 times 1 minus x. Same thing, distributing the bottom would give me x minus 2 divided by minus 1 times 1 is minus 1, minus 1 times minus x would just be x. So this would give me x minus 1. So they're exactly the same. Okay, so it's a standard piece of algebra, one that you should certainly be familiar with. Okay, so what should we do next? Let's do an interesting property that's very important and you'll be intuitively aware of, but you've maybe never had it really carefully explained to you. And it's very useful and it turns up a lot. So imagine I have two numbers, a and b, and imagine the product is equal to 0. Well, what does that mean? That guarantees that at least one of the two is 0. So either a is equal to 0 or b is equal to 0. It could be both, right? So when I say or, it could be and as well, right? So it could be both. So this property, very important, is called the ZeroProduct Property. And it does turn up an awful lot. So ZeroProduct Property. So let me show you a classic way that it turns up. So if we have, let's say, an equality like this, 5 times x plus x squared is equal to 0. Okay, so that's a product of two things. It's a product of 5 and this expression x plus x squared. Now, 5 is non-zero, so that forces, by the ZeroProduct property, so I'll write it in exactly the same way, it forces x plus x squared to be equal to 0. You could also see this, I suppose, by dividing both sides by 5, and 0 divided by 5 is 0, but let's do it with the ZeroProduct property. Next, well, this is if and only if we can factor this, take it a power of x, so we're doing the distributive law backwards. So slightly wrong here, aren't I? It's 1. This has to be equal to 0. So now this is if and only if, well, either x is equal to 0 or 1 plus x is equal to 0. That really is the ZeroProduct law, or ZeroProduct property. But now we can move that 1 across the other side by taking 1 away from both sides. This is x is equal to 1 or x is equal to minus 1. I want you to pay close attention to how I've written this. I've done it very slowly, one step at a time. I'm not invoking anything fancy. At every stage, I'm being real careful, right? So here, this is the ZeroProduct property. Here, this is just factorization, which I'll talk about more in a later video. Here, this is the ZeroProduct property. And here, if you want, we're invoking this piece of algebra, right? We're doing a plus b is equal to c if and only if a is equal to c minus b. You see, at every stage, I want the next piece to follow in a very simple manner. So everything I'm doing here is trying to make sure everything is done slowly, methodically, where every step is completely justifiable using your basic properties. So very nice. So we've got that. So now another really important property is the following, which actually does follow from this. We won't worry about that. If a number is non-zero, then the following is true. A times B is equal to A times C guarantees that B is equal to C. Now, why is that true? Well, if you want, you could divide through by A or multiply by 1 over A on both sides. That would cancel it off. You're left with B times C. It only works, of course, if A is non-zero, right? This is not true if it's 0. For example, 0 times 1 is equal to 0 times 3. 1 is not equal to 3. So it has to be non-zero. So this is called the cancellation property for obvious reasons. The cancellation property. So let's do an example, shall we? And I want to do one that's a bit subtle. I don't want it to be just completely simple. So imagine we're trying to find, I should also say, the examples I'm doing here, there are different ways to do them, generally speaking. That's one of the things about algebra. To get from A to B, there may be several different routes. But again, they should all be done slowly, methodically, where every step is completely elementary. So let's do this guy. Imagine I'm trying to find an x with this property. So first of all, 7x, well 7 is non-zero, so I can cancel it off. So this is what? This is the cancellation property. I'll write it as CP. So then, well, what can I do? Let me rewrite this as follows. So this would imply that x cubed minus x is equal to 0. Okay, so that, if you want, let's be real careful about this. This is the statement that, it's the same as the one above. A plus B, let's get this right. Implies that A is equal to C minus B. It's exactly the same logic. We're basically moving the x to the other side by taking negative on both sides. So next, we can factor this, thankfully. It's distributive law. X squared minus 1 is equal to 0. I suppose at this point I could invoke the zero product law, but I can factor a bit more, remember? Because x squared minus 1 is x squared minus 1 squared, which is the difference of two squares. So this is x plus 1 times x minus 1 is equal to 0. So now what do I have? I've got a product of three things. Now the zero product property is about the product of two things being 0, but it also works for the product of three things. At least one of them has to be equal to 0. So this now guarantees what? This guarantees by the zero product law, so I'll write that as zero product here. This guarantees that x is equal to 0, or x plus 1 is equal to 0, or x minus 1 is equal to 0. And again, the same piece of algebra is up here. Now guarantees that x is equal to 0, or x is equal to minus 1, or 1. So there are three possibilities. Now, there's a classic error that I see made here an awful lot. So let's go up here a second. So what I'm going to describe here is wrong. So wrong. So let me explain something that's incorrect. So something that you could do would be, or it maybe looks like you could do, would be right, okay, 7x is equal to 7x cubed. Okay, so now that guarantees what? Well, 7x is equal to 7x times, write this a bit better, 7x times x squared. So now you might think, okay, we'll apply the cancellation property and get rid of that 7x. So this is 1 now would be equal to, well, just x squared. And then what would that mean? Well, you've got two options. You go through various pieces, but this guarantee x is equal to either plus or minus 1. So what's happened here? We've lost something. We've lost something. We've lost the 0. Where is the 0 gone? The problem is in the application of the cancellation law. Right here, the only way this works is if 7x is non-zero. I can't cancel something off if it's 0. Okay, so what does that mean? So i.e. x is equal to 0. So this is not correct, right? This does not imply this. The other way actually works, but not this way. So this is no good. So more than anything, you need to be very careful about applying laws of algebra. You're dealing with numbers. I can't stress that enough, right? And if you're making some statement about letters, it has to be true for any number that could be put in the position. So this cancelling off will not work if x is equal to 0, so it is an invalid piece of algebra. You need to be very careful not just to blindly do algebra without thinking about what you're actually doing, which is looking at properties of numbers. And if there's some number where the piece of algebra fails, that needs to be treated completely separately. Right? This is something that's difficult, but requires a lot of thought. And it's in many ways the key to doing well in university mathematics is attention to detail, and especially the cases which don't fit completely neatly into the standard pattern. So this is a good example of being careful. Okay, so let's go to fractions, shall we? And think about algebra with fractions. Because this is something that is difficult, again, and lots of misconceptions about how to do algebra with fractions, especially when we're kind of doing arithmetic with them or summing them and things like that. Okay, so first of all, a over b is equal to 0. This is if and only if a is equal to 0. All right, very standard fact. Again, always, and this is going to be running through this, we can't have b as 0 on the bottom. It doesn't make sense, right? That notation means nothing. So as an example, if you had x minus 1 divided by 5 is equal to 0, this forces, you could do this in several ways. You could multiply through by 5, all the rest, but this forces x is equal to x minus 1 to be equal to 0, and now you just add 1 to both sides, x is equal to 1. Every step, nice and simple. Next, and this is quite a thorny issue with fractions, when we write down a fraction, it's not unique in the sense that the same number can be represented by two different ratios. So this is exactly the same basic issue as a half being expressible as 1 divided by 2, or indeed 2 divided by 4. So this is very important. Two fractions give the same number if and only if. So there are two things you can do. You can basically, well, there's one thing you can do really. You want to multiply both sides by BD and then simplify. And if you do that, you end up with the following equality. You end up with AD has to be equal to BC. And again, we're making the assumption here that B does not equal 0 and D does not equal 0. Otherwise, the left-hand side doesn't make any sense. So let's see this in action, in an actual situation. So we have x plus 1, let's say divided by 5, is equal to x plus 2 divided by 3. And imagine I want to find all x that do this. Okay, so this is if and only if what? Well, 3x plus 1 is equal to 5x plus 2. Very nice. So let's distribute these. 3x plus 3 is equal to 5x plus 10. Let's use the standard algebra of moving things around with sums and differences. So this would give me 3 minus 10 is equal to 5x minus 3x. So this is now if and only if minus 7 is equal to the distributive property, 5 minus 3 times x. This is if and only if minus 7 is equal to 2x. And now finally, we're going to divide through by 2. Minus 7 divided by 2 is equal to x. So every stage simple. Everything in if and only if statement, they all are completely equivalent to each other. Very good. Okay. So that tells us when we have two fractions that actually give the same number. There's a slightly different way to look at this as well. It is the following. So if I give you a fraction a over b, and I give you another fraction ca over cb, they're always equal to each other, assuming, of course, everything makes sense. So as with all of this, we have to have b and c non-zero. Okay, and in particular, this has the strong consequence. It's not really a consequence, but it's another thing to be aware of. A divided by 1 is equal to A. Just a very simple fact, these two things together. So just as an example, if I do x squared, or sorry, let's do x cubed plus x divided by x squared plus 1. Can I simplify this a little bit? So first of all, let's write this as, let's do x squared plus 1. Let's factor out an x. And the bottom is exactly that, if you notice. This is x squared plus 1 times 1, if you want to really labour the point. Now let's make an observation. If I'm going to kind of cancel the top and bottom like this, I need the top and bottom to be non-zero. And in this situation, I'm really lucky because x squared is always non-negative, right? It could be 0, but it's greater than or equal to 0. So that means x squared plus 1 is greater than or equal to 1. So this term in here is non-zero for all x. Brilliant. So that means I've got nothing to worry about. That basically means the following. It means I can cancel it, give x over 1, and of course that's just equal to x at the end of the day. So this expression is completely identical to x. But I need to be a bit careful, right? In particular, as a warning, this wouldn't work, or this would only partially work, maybe. For if I did, let's say, x cubed minus x divided by x squared minus 1. You see, in this case, it would be x, so it would be exactly the same. It would be x squared minus 1 times x, all divided by x squared minus 1 times 1. But I can't just cancel that, right? I can't just cancel it because what about if x is equal to plus or minus 1? If x is plus or minus 1, x squared minus 1 is 0. It would be 0 over 0, which wouldn't make sense. So this isn't really equal to x, right? It's only going to be equal to x. So I'll be very careful. Only equal x if x does not equal plus or minus 1. Whereas the top is fine, right? Any value of x, it's always the same. But if I'm going to write down this piece of algebra, I do need to keep in mind that it's only, if I was to say this last expression is equal to x, I would have to include the caveat that as long as x is not equal to plus or minus 1. So it's kind of a subtle point. It turns up a lot when you're dealing with, well, we'll see when you're dealing with domains of functions in later videos. Okay, so subtle points to be very careful of. Next, let's think about my algebraic operations. So algebraic operations, I've basically got two that I should worry about, addition and multiplication. Let's do multiplication first because it's much more simple. A divided by B multiplied by C divided by D is nice and simple. It's exactly what you'd guess it is. It's A times C divided by B times D. Right? Super duper simple. Let's do a very easy numerical example. 6 divided by 7 times, let's say, 14 divided by 6 is equal to 6 times 14 divided by, let's do 6 times 7, just to write it like this. But now I can cancel off because 6 is non-zero, so this is 14 divided by 7. Of course, that's equal to 2. Just a simple example. Some consequences of this are that taking inverses of fractions kind of turns them on their head. So if I have 1 and I'm taking the inverse to A over B, it's B divided by A. That's basically because if I multiply B divided by A divided by B, it would be AB divided by AB, which is 1. So this has a really important consequence when we're dealing with ratios of fractions. So this is A over B multiplied by C over D, and of course you could write this as, have I just done the wrong thing? I think I have. You turn this one upside down. So this is equal to AD divided by BC. Okay, as an example, x plus 1 divided by x, let's say divided by 7x over 6. Okay, so what does this turn out to be? It's very important, I think, to put the brackets here, or the parentheses, because it can be very confusing what's the true denominator and what's the true numerator. So what's this? This is x plus 1. It's not so bad for the next stage, but when you're writing like that, it's a good idea. 6 divided by 7x, and now you could simplify this as, well, 6 times x plus 1. We could distribute 6x plus 6 divided by 7x squared, if you want to simplify things a little bit. Of course, we're assuming here x is not equal to 0, otherwise we'd have problems with the denominator. Okay, so multiplication is not too bad. It's addition which is more complicated. And let me kind of go through addition quite carefully. So let's take the following. So let's do A divided by B, and let's add it to C divided by D. Now what I want to do first is to actually work out what this is from first principles using my foundational properties. So first of all, the fractions are pretty confusing. Let's make the denominators the same. And to do that, let's basically re-express these with the denominator BD for both of them. So that will involve multiplying the top and bottom of the first by D and the top and bottom of the second by B. So AD divided by BD plus BC divided by BD. Okay, exactly the same. I'm assuming here B and D are not equal to 0, of course. So B and D are non-zero, as always. So next, what do I have? Well, here's kind of the fancy part. I can rewrite these in multiplicative notation if you want. So AD multiplied by 1 over BD plus BC multiplied by 1 over BD. So making the denominators the same allows me to do this. But now I can see I have the distributive rule. So this is equal to AD plus BC multiplied by 1 over BD. But now I could rewrite this in fractional notation. AD plus BC divided by BD. So you see this rather nasty looking formula, if you want, for the sum of two fractions follows from the basic properties. Let's do a quick example, shall we? So if I had 1 over x minus 1, I was plussing minus 1 over x plus 1. Okay, so let's do this really carefully. It'd be 1 times x plus 1. I'm going to go through the actual procedure. Plus minus 1 times x minus 1. All divided by, actually I won't, I'll just write down the formula. So this is x minus 1 times x plus 1. So now let's do the top. This is x plus 1, the distributive law, minus x, minus 1 times minus 1 is equal to plus 1. All divided by, let's do fancy stuff, it's the difference of two squares, x squared minus 1. The x's cancel on top. 1 plus 1 is 2. 2 divided by x squared minus 1. Everything done very carefully. Okay, so special case of this, which is worth pointing out. A special case, which very important, is when the denominators are actually the same. Then there's no real need to go through this whole procedure because we can do the algebra from the get-go. So if this happens, then the following is true. A over b plus c over b is very nice. It's just a plus c divided by b. Kind of makes sense, right? If you have, I don't know, 3/8 of something and 4/8, if I have it all together, it would be 4 plus 3/8, 7/8, right? So it works. But you've got to have the same denominator. And a warning here. A warning. Very important. Don't make the mistake of thinking that the sum of two things is the same as how products work. It is not the sum of the terms on top, the numerators and the denominators. That is horribly false. Let's do an example. 1 is equal to a half plus a half, isn't it? Okay, of course. But if I was to use this rule, 1 plus 1 over 2 plus 2, what's that equal to? 2 divided by 4, that's equal to a half. They're definitely not equal to each other. Okay, so again, if you're using a piece of algebra and you're a little bit unsure, just feed in some numbers and see if it works. If it doesn't, it's not true. So just to summarize, all of the properties we've gone through here, every one of them is essentially what I would consider to be your core algebraic manipulations, the ones that you do over and over again when you're doing complicated pieces of algebra. They all follow from our really fundamental things at the very start in the previous lecture, in the previous video, but these are the ones you do repeatedly over and over again. The skill in doing algebra is essentially mapping out a route using these simple pieces, but to have any hope of mastering algebra or getting really good at it or good enough at it is to really be conscious of these different principles, these different manipulations, and the subtleties. Things like this, trying to cancel off something which is 0 doesn't work. So you've got to be careful, right? But the core thing to understand is anything you do with algebra must be doable with numbers. If it's not, that needs to be kind of treated separately.